Hello everyone. I'm Dr. Shakira Tanvi, presently working as an assistant professor in the Department of Mathematics, Government First Grade College of Zalpur. This is the first video lecture towards the mathematics course for BSc third semester students of Gulbarga University, Kalaburgi. This is session 11. Here I'm going to cover the topic Euler's F function and corollary 3 Euler's theorem, corollary 4 Fermat's theorem. Before moving on to the next topic, let us recall what is Lagrange's theorem. The order of every subgroup of a finite group is the divisor of the order of the group. That is, let G be a finite group and H be any subgroup of G, then order of H always divides the order of G. Some consequences of this Lagrange's theorem are there. That is, first corollary, the order of every element of a finite group is the divisor of the order of the group, and the corollary 2 is, if G is a finite group, then for all A belongs to G, A raised to order of G is going to be unity. Now we have the definition of Euler's F function. For all positive integers n which is strictly greater than 1, Euler's phi function is defined as phi of n is equal to number of positive integers which is less than or equal to n and relatively prime to n. Here phi of 1 is 1, for example phi of 8. The numbers which are less than or equal to 8 and they should be prime. Prime number is 1, a number which is divisible by 1 or by itself is called as a prime. So the number of numbers which are less than or equal to 8 and which are prime are 1, 3, 5 and 7. So phi of 8 is 4. Next we have corollary 3, that is Euler's theorem. If n is a positive integer and a is relatively prime to n, that is a comma n is equal to 1, then a raised to phi n is congruent to 1 mod n. We know that the set G of all positive integers relatively prime to n form a group under multiplication modulo n. Let this group be G. This group has phi n number of elements. Let us say O of G, the order of G to be phi of n, and let A is equal to Qn plus R, where n, Q is the quotient, R is the remainder, where R is lying between 0 and n. Since A comma n is 1, R comma n is equal to 1, which means R belongs to G. By corollary 2, what this corollary 2 says here, if G is a finite group, then for all it belongs to G, A raised to order of G is equal to unity. So using the corollary 2, R raised to phi of n is equal to identity of G, that is 1, calling this as equation 1. Since A is equal to Qn plus R, which means A is congruent to R mod n, which implies A raised to phi of n is congruent to R raised to phi of n mod n. Again, A raised to phi of n is congruent to 1 mod n by using the corollary 1, hence the theorem. Next is corollary 4, that is Fermat's theorem. If P is a prime and A is any integer, then A raised to P is congruent to A mod P. Here we have got two cases. First is if A is relatively prime, the second case is if A is not relatively prime to P. If it is relatively prime, so A comma P is congruent to 1, then by Euler's theorem what we have, A raised to phi of P is congruent to 1 mod P. Since phi of P is equal to P minus 1, since P is prime, so A raised to P minus 1 is congruent to 1 mod P. A dot, just multiply A on both the sides, so A dot A raised to P minus 1 is congruent to A dot 1 mod P. Since the base is same, so powers can be added, 1 plus P minus 1 will be A raised to P. So A raised to P is congruent to A mod P. Hence the theorem. Next the case is 2. If A is not relative prime, then the equation will be A comma P is not equal to 1. Since AP is not equal to 1 and P is prime, which means P is divisible by A, or else the remainder will be 0. So A is congruent to 0 mod P. So A raised to P is congruent to 0 raised to P mod P, which implies A raised to P is congruent to 0 mod P, calling this as 1. Since P divides A, P can divide negative of that also. So it is A is congruent to 0 mod P or 0 is congruent to A mod P, calling this as 2. From these two equations, A raised to P is congruent to A mod P, hence the theorem. Corollary 5. If G is a finite group of order n, then for all A belongs to G, A raised to n is equal to E. Let order of A be suppose m, which means A raised to m is equal to E, calling this as 1. Using corollary 1 again, order of A divides the order of G, m divides n, so Order of G is n here, so n is equal to mq. Consider a raised to m is taking a exponent here. A raised to n is equal to a raised to mq. This a raised to mq can be written as a raised to m whole raised to q. So this a raised to m from this equation can be written as e raised to q. This is by equation 1. So a raised to n is equal to e. That is your corollary 5. Next we have corollary 6. A finite group of prime order is cyclic and hence it is abelian. Let G be a finite group of prime order. Let order of G be P. P being a prime, let A is not equal to E, which belongs to G, and consider a cyclic subgroup H generated by A, that is H is equal to A. Then by using again Lagrange's theorem, the order of H divides the order of G, which implies order of H divides P. Since P is prime, it has no divisors other than P and 1. So order of H is equal to P or order of H is equal to 1. But order of H is not equal to 1 since A, comma E belongs to H. So order of H is equal to P, order of H is equal to order of G, hence H is equal to G. Since H is a cyclic, G is also cyclic and hence G is abelian. Next we have corollary 7. A finite group of prime order has no proper subgroup. Let G be a finite group and order of G be P, suppose, and P is being prime. Let H be any subgroup of G. Then by Lagrange's theorem, what we have, order of H divides order of G, which means order of H divides P. Since P is prime, again it has no divisors other than P and 1. So order of H is equal to 1 or order of H is equal to P, which is equal to order of G. So H is equal to U or H is equal to G, hence G has no proper subgroups. So here we have worked examples. Find all the right cosets of the subgroup H is equal to 0, 3 in the group Z6 plus 6. So first we'll find the order of Z6, which is 6, and order of H is here 2. So the number of all distinct cosets can be calculated by order of Z6 by order of H, which is 6 by 2, that is 3. So these three cosets are given here. In a similar way, we have to find out list all the subgroups of Z9 and plus 9. Similar way, we have to calculate in this. Next, find the order of the cyclic subgroups at 12 and plus 12 generated by 3. Same way you have to follow it for this example 4 as well. Next, we have the multiple choice questions. Find the order of the cyclic group of Z30 plus 30 generated by 25. Here the answer is, you have to find out in a similar way. So order of H here is 6 here. Next, a finite group of prime order has no subgroups. Whether it is true or false, the answer is true in this case. Next, we have every finite group of composite order has proper subgroups. That is also true. Next, any group of order 5 or less is abelian. The answer is true in this case. Next, we have what is the value of phi of it? We have already calculated, that is 4 here. So these are the references. Thank you for watching.